Good evening and welcome back to Vegas October 1 Sounds. Been quite a while since I've published a video. In the last couple months, in addition to having to deal with all the craziness in the world, I've been working on a couple of projects. One of them involves the signal analysis on the Lost Uber video. And here a while back, both 5x5 News and Sean Graham and WAPTech and even Brian Shields published some stuff on a video that was recently discovered that had been used or has been used by by a Las Vegas Police Department and various other fire departments and whatnot there in Vegas. And finally it showed up in a presentation that one of the assistant fire chiefs was presenting. So I took the original or the presentation video and narrowed in on the region that contained a few clips from a recording that was made by a Uber taxi driver. Now in the presentation, the assistant fire chief doesn't play the Uber recording in its entirety, which is a shame, because this is the only known recording that covers the first shots through covers the first shots all the way out to the 8th volley, but it's the only one that covers the first shots and volleys 1, 2, 3 close to the Mandalay Bay. And this video is going to be an ad hoc overview of what I've been doing and working on, and I'm going to show a few things that I've discovered. And later on, I'll produce an official series of videos on this in which I'll cover everything in detail, including all the shooter localization that can be done from this video. So with that said, let's get started. Now since we last spoke, I've started using Scrivener to produce and keep track of my notes and documents on various research that I do. And this is the Scrivener session for the Lost Uber video. This project does not cover shooter localization, and other than mentioning what I've been doing with it, I'm not presenting any of that tonight. In fact, what I'm going to do is give an overview of the thing, and I'm not going to cover any of the volleys in detail except the first 6 shots. And I want to do that because in the video itself that the fire chief presented, they noted that there were more shots than what we had thought existed. And I'm going to cover that in quite a bit of detail and show you exactly what I found. It's not what I expected, it's not what he showed, and it's not what anybody else necessarily has expected. And I've spent a great deal of time looking at this stuff, and there's a great deal of time left because I like to cover all my bases and cover all the possibilities and options. And I won't make a definitive statement, but I'll show you where I'm at. So with that said, let's take a look. What I did was, after I extracted the video portion that was relevant to the Uber thing, I took a very careful look at where the taxi was when the shots occurred, and then I plotted it on just one of the Google Maps thing. And in fact, I have a project going where I'm making a Google map to share with people that'll have this route and bunches of other information on it that you can access through the map. But that's somewhere down the road. I've also got a Google site going that's a little bit more comprehensive than just this, but that's a couple months out still, and where I'm collecting all my work and putting it on the web for people to see so that they don't have to sort through all the YouTube videos. And well, anyway, there's a lot coming in the future, but let's just focus on this one tonight. So the taxi driver obviously just didn't show up on the scene. They had to come into Mandalay Bay through the normal routes. But the first clip that is shown occurs in this underneath this portico where the taxi drivers collect. Now this thing has 2 levels. It has a top level and an underneath level. And you distinguish the two, or I did anyway, by looking at them by the fact that on the roof or on the ceiling of where you drive, the upper level has signs that are clearly readable as you approach, and the bottom one doesn't. And so this taxi driver was actually on the bottom. He was underneath this. Well, let's get some drawing going here. Can't work without drawings, can we? All right. So this little platform driving up here, that's on the top, and then down underneath it, which you can access by many ways, but you can come in here, drive in over here, and go in through there and come around and go there, and it goes right under there, and then it keeps going underneath and underneath and underneath, has a similar structure, and comes out, and then it comes out around there, and then it meets back up right here, just about where volley 1 was. So anyway, the taxi driver is beneath this overhead driveway, as you would call, and it's kind of in an isolated position, and because of that, the signal is attenuated or reduced massively, and I'm going to get into that in a little bit. And so there's no direct path for the sound to reach the microphone, which is in the middle of the car. It's a Golux type camera. The passenger window, I believe, is rolled up, and so for the sound to come in through the driver's side, it has to go in or around or over the top of the car or off the walls and in through the ceilings, and so it's really low quality. There's a lot of reverberation. So there's a lot of analysis and filtering that has to go on. Okay, and then anyway, once the first shots are done, the car moves on, and it eventually ends up here where it's been marked 1. Now you notice in this volley that the driver window marked by the little yellow arrow here is on the same side as room from where the shots came. And so the signal has the possibility of going directly in the window, and therefore the signal there is much larger in amplitude. And then the taxi driver moves on and goes down, and just about as he's passing the tram area is when volley 2 occurs. And again, the driver's window is on the side that's the shots could potentially be coming from. And volley 2, and then, well, let's just cover it. So then it goes on and makes the corner out onto Mandalay Bay Drive, and in that case, the driver's window starts by being directly, exposed to the gunshots coming from the north wing, and then it curves around, and the driver's window is on the outside away from it. So the sound coming from over here at the Mandalay Bay is going to have to go over the top of the car and back in through the window, which means that it's going to lose some of its signal strength. And then as we go down here, it moves on down to almost at the stop light, and volley occurs in that region. And then after the light turns green and goes across, the 308 shots occur, and then it continues on almost to the corner down here, and that's where volley 5 occurs. It pulls a Huey, comes back up towards the venue itself, and volley 6 is occurring, and the cop comes over and tells him to get the heck out of Dodge, and so the taxi backs up all the way back around to the corner here, and it stops essentially, and that's when volleys 7 and 8 occur. So for volleys 7 and 8, the the driver window is on this side to the right, which is kind of away from where maybe the Mach waves or the supersonic cracks would be coming from, but kind of still okay direct for the muzzle wave. So for all of these things, then I would expect that volleys 1, 2, and 4 are going to end up being the strongest, with 3 being pretty weak, and 7 and 8 out there would depend upon the route that the bullets take in terms of how loud the Mach wave is. Alright, so let's take a look at that phenomena, and there's 2 signals in this. It's a stereo recording and it's a piss poor recording, and The first thing I noticed is that the overall amplitude of the signal only uses about 10 or 12% of the dynamic bandwidth of the recording. Most recordings are what they call normalized. That is, the post-processing of the video or the audio, it will take a look at all of the audio throughout the entire recording, and it will say, okay, this is the maximum that occurs, and then it will say, okay, I'm going to go ahead and make the maximum signal be the maximum amplitude on the recording. And so therefore you get the greatest possible use of the dynamic range of the encoding software. This video does not do that. It only uses the 10% or 12% available to it, which means that all of the gunshot sounds now are compressed into a very small region of dynamic range, which means that the low end is not as far removed from the high end as would occur in most other Vegas recordings. I don't know why they did that. I don't know whether if it's just a screw up or there's something else going on. And again, there's two channels, and the two channels are not the same. In fact, the channel that's on the right hand side of the, or channel 2 on the right hand side of the camera, has a substantially different amplitude response and frequency response. And there's something going on there which I haven't yet quite figured out, but I'll show you a little bit about it when I show you. Well, let's just go on to it. Before we move on too far, let's show you the what I call the angle of fire that these shots must have taken. So for the here I've in the center located room 32-135, and then over on the pink one, room 32-134, and the only shots that we think occurred out of 134, of course, are the 308 shots marked with the purple line. But for all the others, which are marked with red, light green, yellow, white, and again red, we can see that volley 3 and the first 6 shots are almost at 90 degrees to the direction of the bullets, which should have come directly out of the window and head towards the venue. And there's a special sort of phenomena that happens when that angle is at such a large 90-degree thing, and it reduces the intensity of the muzzle such that for volley 3 and the first 6 shots, you can expect that their signal will be reduced over, or over what say volleys 1 and 2 would be. So if we think about logically what must have happened, there's a shooter paddock, let's say just like paddock for argument's sake, inside a room, and the bullets and the sounds from the gun have to come out the window, and we don't know precisely how big the opening is in the window. In fact, I believe that the size of the opening changed during the first 6 shots, and I'll explain why later. And so we don't get the full impact of the gun because some of the sound coming from the gun as he is inside the room, i.e. he's not hanging the gun out the window, a good portion of the intensity of the sound is captured in the room, and only a certain portion of that full gunshot sound comes out the window. And the further back in the room he is, the less of that will come out the window. And the further back in the room he is, the more directional it becomes. That is, it comes more straight out the window the further back in the room it gets. Now, that's not exactly a true statement, because the lower frequency muzzle blasts, when they come out the window, tend to spread out in all directions, just like good little sound should, not in perfect spheres, and that's something I'll have to cover in another video, and I actually have some videos already in my channel that explain that process. Basically, the sound does not come out the window evenly in intensity in all directions. In fact, there's a substantially large region close to the window on both sides of the travel of the path of the bullet that are reduced in volume. And that's proportional to where the shooter was located and the size of the opening and the intensity of the sounds. And we'll be talking a little bit about that. But for the first 6 shots, I want you to notice that for the sound to reach the camera, it has to come out the window. It has to take this 90-degree curve here, angle, and it has to go under this overpass, and then it has to go over the car and in the window of the driver's side. Now, some of the sound will hit the closed window on the passenger side and it'll vibrate in there. But the higher frequency supersonic cracks, or Mach waves as they're called, are quite directional, and they're going to have a very difficult time reaching this taxi for these first 6 rounds. For all of the other locations, well, 3 is a little difficult too, but they can still do it. But for all these other locations, the supersonic cracks or the Mach waves, it's just a straightforward process to get in to reach the vehicle, and they may have to diffract around the windows to get inside, but they don't have to, go under the overpass, and they don't have to go 90 degrees to, from where the travel of the bullet is. All right. So, having said all that, what does the signal start to look like? Well, as you're well familiar, those who are familiar with my channel, there's a lot of detail we can get into. But first off, let's look at some of the energy graphs. And energy is, kind of proportional to the power of the shot, and it's kind of proportional to the loudness. Not really, but kind of. So if we look at some graphs here, and we plot both channels on one graph, and the yellow is channel 2, which would be the channel that doesn't respond as well as channel 1, which is on the left side of the camera. And here we can see that for the first 6 shot, there's a pretty big difference between the red and the yellow. And for volley 1, there's a pretty big difference. Then for volley 2, they're pretty similar. For volley 3, they're pretty similar. For the 308 shots, there's this small gap between them, but essentially they're the same. And then they essentially stay the same until we get out here to volley 6 and volley 7, and then there becomes some differences. So, is this a channel phenomena, or is this something happening in the environment that causes these two signals to become different? And I think it's a little bit of both. First off, I think that there's less amplification being applied to channel 2, and then also I think that there's something to do with the angle between the channel 2, i.e. the right side of the camera, and the window and the person in the car that causes some of these differences in the channels to be recorded, to be there. So if we take a closer look at this now, and we look at each shot, each volley or groups of shots, and we'll start, and there I just did it without all the markings above. See up here marked where the shots were in gray. Down here I haven't. You get a little bit picture. I'll just hold it there for a minute so you can see it. And on the left you'll see the signal strength, or the amplitude of the recording, and the amplitude is a reflection of the pressure of the sound that strikes the microphone, which is a direct indication of intensity of the field, or the pressure field that the sound produces against the microphone. And here we see that this is a scale which, when reached at full scale, is 1. And here we can see that for the first volley, right, well, let me mark it. Okay, the first volley occurs right in this region. And it's somewhere averaging energy, somewhere, oh, I don't know, right around this region, which is about 0.01, and in this case it's going to be volts, but just 0.01, it's a number we can work with. And you'll see that the second channel over here varies a little bit away from it. You'll notice one thing though, is that where these first 6 shots are is down here. Okay, now back up here at 0.01, that's 1/10 the full scale, or excuse me, 1/100th of the full scale amplitude. Okay, you have to get that in mind now. And this down here is 1,000th of the full scale amplitude. So there's quite a big gap there. And did I say that correct? Because this scale, no, these are average energies, not peak amplitude. All right. So then we go down and we go look very close at the first 6 shots. And here we can see, and I left the little things up there, that's where volley 1 was, is that these are the first 6 shots, the average energy for them. And you can see that the yellow channel essentially records nothing, and that the first channel, channel 1 on the left hand side of the camera, and this is where on the right hand side where volley 1 occurs, and you can see there's just these little bumps going along there. Now, having worked with this for such a long time, I can tell you precisely, you know, where these shots occur, but just looking at this graph overall, you'd think that there wasn't much going on. And so this intensity, or the lack of intensity for these first 6 shots, is a real conundrum, and it takes several different careful analysis to explain why it's so low. For example, the overhead platform on the top, that's the driveway on the top level, will probably reduce it by a factor of 2. That is, either a Mach wave or a muzzle wave coming from above and hitting that will have to go out around both sides of the overhead and then come back in and reach the signal and reach the taxi, and in doing so it'll probably be reduced by 1/2 of the original signal or more. And then similarly, to get inside the car, it's going to have to do something kind of similar. It's going to have to go over the car and then refract back into the window, and then make some kind of obtuse angle to reach the camera, which is in the middle of the dash up near the rear view mirror. So again, there it's going to be cut in half. So we got two magnitudes of 2, so that's at least 1/4 the signal that was could be recorded from the window itself. And then you have that effect of the 90-degree angle and the diffraction out the window, which it can be almost 98% of the signal lost at that angle. So here we're talking about 98% of the signal lost divided by 4. Well, anyway, if you lose 98% of the signal, you got 2%. You divide that in half. You got 1%. You divide that in half again. You got 1/2 of 1% of the signal actually might reach the car, and that's why this signal is so low. Versus having a straight shot out the window to the sound at not a 90-degree angle, but almost perpendicular to, or right in line with the bullets, then you're going to have nearly 100% of the signal from both the muzzle wave and the Mach wave, and it's going to come almost directly into the car, and that's what you see with volley 1 as it comes. And so, but these numbers on the left indicate more of the fact that this signal was not normalized, and therefore there's a factor of 10 against us already. That is, they only use 10% of the dynamic range. Now, if I'm getting kind of technical, you can skip this part, but we have to at least set the stage for the things that I have to do later on, because to do a good job of looking at this signal, I'm going to have to amplify it and do some filtering, because I can't look at such a small signal and get enough detail out of it. And the sad part is that when you amplify the signal, you also amplify the noise or the sound floor with it, which brings us to, well, let's just go on here. So if we look at volley 1, you can see that it's pretty flat across the entire range, except that the right hand side of the camera, channel 2, has this discrepancy here at the first 30 shots or so. And then it finally catches back up. And I'm not going to talk about why on those things tonight. Let's move on to volley 2. And here you see that both channels record, something. Now, volley 2 is different in that it's not flat, and that's because there are regions of volley 2 where there are no shots being fired, so obviously the average energy would jump down. Then if we look at volley 3, the one that's going around the corner, you can see some fluctuation here at the start of volley 3, and then it pretty much levels off. But if you'll notice, volley 3 comes in around between 0.001 and 0.005, and volley 2 came in much larger. So volley 2 has a much larger intensity than volley 3. And if we were to go back over to volley 1, we'd see that it's comparable to volley 2, but not quite as loud in all cases. Alright, so that brings us to volley 4, which they're out in the street by this time, and the driver's window, which is the at least partially open window, is pointing away from Mandalay Bay. And so we get volley 4, and there's not much difference between the two channels, and it has, it starts out kind of low and then gets kind of high for whatever reasons. Alright, now the 308 shots, which occur as the car is moving through the intersection. And the 308 shots are these little bleeps here. And as you can see, both channels and record about the same, and they're visible. They're not real large. Over here is where a siren occurs. That's why it's so loud. And the reason these are small is because there's only a single shot. There's not this cumulative effect. These energy graphs are averaged over a tenth of a second. So in that tenth of a second, there can be up to 10 shots on a regular, consistent volley, and therefore the average energy is much larger than just having a single shot come by, which can explain why the graph for the first 6 shots is also kind of low. But here you see that the first 6 shots are not these nice little peaks, which I'm going to have to explain in detail here in a little bit. Alright, that brings us to volley 5, which occurs as Mandalay Bay Road turns left onto Giles. And so here you can see that volley 5, which consists of 3 bursts, is not real consistent in intensity at all. And in fact, some of these peaks are not associated with the gunshots, but associated with the sounds that occur in the background. And we'll see that when we look at the spectrograms. Alright, volley 6, which is after the taxi has made its U-turn and headed back towards the Mandalay Bay, and runs into the cop, who bangs on the hood, screaming and hollering, telling him to go back the other way. Now this poor woman is totally confused. She's got no clue what's going on or what to do. And she ends up calling what I believe to be, her significant other, and talks to him before the whole show is over. So this is volley 6, and volley 6 has a burst out the front and a burst on the rest of them out there. And there's massive variations in intensity throughout the volley. And once again, this is mostly due to the background. The intensity of the volley itself is somewhere down here on the 0.005 scale. So nothing particularly interesting at the moment there. Volley 7, as you can see in this case, the background noise is not loud here, but for volley 7, the two channels have a big difference. It starts out the same, and then the left portion of the camera audio goes up considerably, and the right portion goes down. And I'll be getting into that when I do the full report on this thing. Remember, this is just kind of a survey or overview of where I'm at, and we're going to focus on the first 6 shots. Alright, and then of course volley 8. And again, volley 8 are pretty similar, and these loud peaks are due to background sounds. Alright, so that's an overview of the average energy. What do these signals actually look like? Well, that depends upon what you want to view. So, where shall I take us? Let's go up to Let me see where I want to start. Okay, well, first we start with what was shown on the video. And this is a clip, or an image from the clip that shows what the presenter called the first 6 shots. And he's marked, let's count them up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 different spikes. Now we can see the different spikes here. Okay? And so I only know, when going into this thing, I only knew of 6 shots that were fired prior to the rapid fire volleys. And so all the videos that I had used occurred, at least at the intersection and beyond for the first 6 shots. And here is, one of those where I have marked the muzzle blast for all 6 shots. So I wanted to get an idea of how the video that this guy was presenting correlated in time to what I know about the first 6 shots. And here I've marked them, and I marked them based upon the timings from an average of timing of all the other muzzle shots recorded in about 20 different videos. And we can see that these arrows on the right hand side of his presentation mark pretty well the last 5 rounds that were fired of the first 6 shots. Okay, and then the very first shot that is known occurs way over here, and so it's amongst this group of things, and he thinks there's a whole bunch more sounds going on there, in there, and he thinks there's some sounds even way out there. So now let's think about this logically. We all know that there were 6 rounds fired at the beginning of the venue. Some people think there had to be something going on prior to. Some people think that there had to be something going on afterwards. Nobody really knows where the down the hall shots at Campos occurred, and that's a big question. And this video would be one that records that. Unfortunately, the only information we have about that would either be from here, which I'm not saying that's what it is, I'm just saying it would be here, or it would occur later, and he didn't put that clip in. But oddly enough, he did put in a reference to say that there was something happening, 21 or 23 seconds after volley 1. Which is, the gap between volley 1 and volley 2 is large, much larger than the other gaps between volley 2 and 3 and 3 and 4. And I have believed up until this point that that's where the Campos shots occurred. And this video should have recorded those in sufficient intensity for me to have made that determination, but unfortunately he does not put that segment of the audio in. But it is marked that something occurs there. I know of nothing else that occurs there. And so that's kind of a, maybe their Campos shots really did occur at 21 or 23 seconds after the volley 1. But we have to explain still then what this would be up here. Okay? So, to confirm this whole process, I took a look at the tall ace of spades, this lost Uber, now we're talking just the first shots, and one other from on the, let's see, that would be the, let me get this right, north is towards there. If we're going north, that would be on the west side of the venue, the one closest to the boulevard. And I took one recording from there, and I compared all the first shots. And let's see here. I got that somewhere. As you can see, I've just got a ton of information on this video. In fact, I'm up to probably close to 80 or 90 pages of images and discussion and all that, and I'm not even beginning to let's see, here we go, 3 video shots, there we go. So I took the waveform plots. These are waveform plots. And here, this is a direct reading scale going from 0 to 1. Actually, 0 to 1 on the top and -1 on the bottom. For the middle one, let's mark that in red. This is the Uber signal, and I made sure that every one of these used the same exact audio scale. This is ace of spades up here, and then this is, well, it's what I call one of the bar. I have 10 different videos, all of which I number bar 1 through, actually there's 14 of them, and this is bar 4 or 5, I forget which, but anyway, it's on the west side of the venue out there in the kill field. And so all these signals are exactly what you would see, and you'll notice that up here, that from the ace of spades, that the peak amplitude on some of these is close to 1. Now remember, the peak amplitude down here for the Uber video is close to 0. So you see already there's a problem with the signal from the Uber video, and I explained that a little bit already. And I'll be explaining what I had to do to make that signal more visible and more manageable. But even still, I was able to mark it just by looking at it. And of course, in Sonic Visualizer, I can ramp the amplitude way up on the waveform to get a good look at it. All right. So anyway, we see that the signal and the signal to noise ratio for the Uber video is just total crap. The signal to noise ratio on the ace of spades, you can see all these sonic cracks and muzzles. The muzzles are marked with M, the sonics are marked with S. But there's a whole bunch of other stuff going around it, but it's still distinguishable. And then the bar ones, you can see it has a better signal to noise ratio than the other two, but it doesn't always record the same exact sounds. But when you line them all up for the muzzles, and you would expect the muzzles to be lined up identically if all the videos were static, that is, they didn't move, and the shooter wasn't moving, and the speed of sound stayed constant, blah blah blah. Now for this video, the Uber video, the car was moving just slightly, so these things aren't going to line up perfectly, but for this scale they should be what's looking to be almost a perfect match. Unfortunately, when I did it, the ace of spades, I moved to the right a little bit, so you can see there's a little shift between them. Otherwise they would have lined up better. But I did line up Uber and the bars, and as you can see, where the muzzles occur is almost a perfect match. Little bit of variance here on the first one, and that's because, like I said, the car was moving a little bit between the first and the sixth shots. The sonic sounds will vary based upon where the recording is, where the bullet went and all that, but since we're at such a large angle to all of the bullet travel, it's going to be close. They're going to line up more closely than many of the other videos, except that bar and ace of spades are not at that large angle, therefore they'll have a different lag. Now let me go back and rephrase that. Uber's at a large angle, therefore the muzzle wave and the sonic wave or the Mach wave arrive at the same time, and the lag is essentially 0. Out here at bar 5, it's right smack dab in the path of the bullets, and therefore the lag is large, and the Mach wave, or the supersonic crack, leads the muzzle wave by a considerable time, probably on the order of 2 or 3/10 of a second. So therefore the Mach wave on the Uber will not line up with the Mach waves on the bar, and similarly for the ace of spades. In fact, the bar and the ace of spades might line up, but as you can see over here, where the Mach wave is prominent on both the bar and the ace of spades, they don't line up, even though the muzzles do pretty well. And let's see if we can get over here on the Ace of Spades and the Uber, the sonic wave is closer, but it doesn't line up perfectly. And that's because each shot is different in terms of the timing of the bullet and the Mach wave. Whereas with the muzzle, since the only thing that governs it is basically the distance between the recording and the shooter, then the Mach wave doesn't have much of an opportunity to take an alternate path, unless like in the Uber video, there is by necessity a path that is indirect. That is, there is no direct path between the microphone of the Uber camera and the shooter, and therefore the path the sound must take to reach that camera is indirect, and because of that there may be some changes in timing. Alright, so here's those three signals. And then what I did was I increased the gain on the Uber one so I could get a better look at what was happening. And we'll just leave those colors up there. And I increased it by a factor of 10. I multiplied it by a factor of 10. And now you can start to see some real peaks in there, whereas up here it just pretty much looked like some flat little blobs in there with no peaks. Now at 10 times the amplification, or the full scale on the left here is 0.1 as opposed to 1 for the other two videos, we can start to see some structure. And we can start to see where each of the gunshots occurred, with the exception of the first. So for shots 2, 3, 4, 5, and 6, it's pretty clear when they occurred at the Uber. It's pretty clear on the other ones also. But it is not so clear when the first shot occurred. Alright, so let's magnify the Uber video a little bit more to see what we can see. Okay, so here I applied the maximum amplification in Sonic Visualizer that I could, which ended up being around a factor of 100. And so now we can start to see some fine structure even in the first, even in the area of the first round, because you can see these little bumps. And so now the question becomes, is that what the original presenter was looking at, and what are they? Okay, are they really other? Could they be other shots, or are they some artifacts of the fact that we're underneath everything and all this reverberation is going on? In fact, at this magnification, you can start to see that each shot is followed by some echoing, a lot of it from multiple different hard surfaces, that generates a bunch of signal there that is not real prominent. Although there are other little things in there, other little signals, like in the case of the fourth shot, where you can see this bump there that's pretty strong. In the case of the sixth one, you can see a bump. There's some bumps in there that look pretty strong. And so we have to take a look at that and figure out what they are. But from my experience, these downward exponentially decaying slopes are basically caused by the signal hitting surfaces and having to come in through indirect means. You'll see this a lot when you're inside a room. In fact, it'll be 10 times worse. You won't be able to see the peak of the signal. You'll just see this, all of a sudden you'll see the signal go way up, and then it'll hold there for quite a while and then have an exponential decay or downward hyperbolic curve. Alright, so if we just give it up and say, okay, there's 5 shots over there and there's not much else going on, we'll need to look at them more carefully later on. Let's focus our attention on what's happening prior to the second shot, including the first one. And so once again, we take the Uber portion and we amplify it again to where, and I changed the scale a little bit on this, to where we have a lot of signal with a lot of noise. Now we have to start talking about noise and noise floor. In every recording, there's random noise that gets inserted into the signal based upon the electronics or the environment or things that are happening. Now that's different than a low signal. And now in this video there's some music playing in the background very, very softly. And that's part of the background sound, not part of the noise. But interestingly enough, there's also been some noise that was introduced into this from the electrical circuits of wherever this was being recorded. Now this is a recording of a presentation that was made from an original video and stuff added on top of it. So somewhere along the lines, the 60 hertz signal from your AC outlets was inserted. In fact, I have a picture. Let's see, somewhere I gotta do a search here up here. There's too much information. All right, example of 60 hertz signal during a cut. Okay. Now those, just ignore those for a moment. The coloring here. As you know, the video itself, consists of a portion of a video and then a gap, small gap, another portion of a video, small gap. I call those cuts. And if you take a look at the signal in the cut, you'll see that this is at large magnification, has this nice little sinusoidal wave, and when you measure it, it turns out to be 60 hertz, and it's there even when there's no cut. It's there all the time, and that's called basically noise introduced by either a poor connection or being in close proximity to a power cord. Let's say you were at a presentation and you were making it with an overhead projector or something, and you had to have power, and your power cord ran right by your recording device that you had laid on the table to record. Well, that strong current flowing through that power cord probably induced an electrical signal in the recorder itself directly onto the electronics, bypassing the microphone, and that's probably what happened in this case. Okay, so that's noise. That would be considered noise. But the music would not be considered noise. Alright. Let's drill down more onto those first shots. We've covered a little bit about the noise, so let's see. Let's clear the crap off this. So now we hop into a panel from Sonic Visualizer. And what I've done here is I've taken Sonic Visualizer and laid out 3 panes. On the top here I have the waveform, and I've made some annotations, and I divided it up into 1, 2, 3, 4, 5, 6 segments. There could be more, but I've only marked 6 at the moment. And then down here in the middle I have my log frequency plot, which is a plot over time of the frequency of the signal. And then down here I have a spectral contrast, which measures the difference in the frequency of the signal over time between what it was. So if there's a big change in frequency, then you have a bright spot on that spectral contrast. And on that spectral contrast you can see that there's some pretty bright lines. I'm going to have to magnify this to get a good look at it. Okay, we are, and not quite that large, I guess. Okay, there we are. A little more. Can't quite get what I want here. Okay, well anyway, these bright lines on the bottom pane correspond pretty well to the muzzle blast. So we can see that we have round 2 and round 3, round 4, round 5, and round 6, and there's another signal out there to the right, but it is not a gunshot. Now, then we have the remainder of all this stuff here prior to the second round. So out here somewhere is the first round. Now in this particular segment there was a lot of processing needed to get to this point. What I did was I took the region of sound that included all of the 6 shots up to the beginning of the video. I extracted that out, I dropped it into Audacity, and I amplified the heck out of various regions of it differently. It wasn't a consistent amplification, and I'll talk about that in a minute. I then filtered out the 60 hertz hum across the entire thing, and then I took the region between, right here is the first shot, I took it just ahead of there where it seems to be, well, this dark region right through here. And I took that as a sample of noise, background noise, and then I did a spectral subtraction. So I've amplified this thing in a non-uniform way. I've filtered out the 60 hertz, and I've also subtracted out what I believe to be the noise, floor noise, or noise floor. So it probably subtracted out a little bit of the music and the hissing from the tape recording itself. Okay, over here are the vocals of that guy talking. I included them in there just as a reference point. But as you can see, I brought the signal level up for all portions of the first 6 shots to much larger than even the loudest gunshot on the remainder of the recording. And to do that, you'll notice that this one region, right here, that looked kind of boxy, you'll see that there's a much larger amount of blue in the background. I had to magnify that one independently and much larger than this one over here. So if this one were 10 times amplification, this one would be 100. Now that's not the actual magnification level. I just, those are just numbers. One is 10 times larger than the other. And to show you where the original volley 1 is, over here you can see it's pretty low in intensity now in comparison to these signals, which used to be almost 0. And I did all that in Audacity, and then I dropped it into the Sonic Visualizer session. Alright, so on this graph, I guess I need to magnify it a little bit so we can see A, just enough to, there we go. A is the guy talking, just a real small tail end of it. B is the region consisting of the first shot. C is background music. D contains shots 2, 3, 4, 5, and 6. E is some anonymous signal there. And then E is more of the music, but it is now louder. Not because of my amplification, but because it's louder on the original recording. So that's a question that we have to ask, is where's the music coming from and why does it get louder? I don't know, maybe the girl is moving inside there in such a way as to get closer to the camera, or maybe she's blocking the sound more over here than she is there, or maybe some gain circuitry is screwing up on the recording. But anyway, we're going to take a detailed look at all of these regions and make a conclusion based upon what's in these signals. So right now, if you're talking, there's a general problem with acoustic analysis. Acoustic analysis is never really finished. There's always more to look at or more to analyze. But the problem is you lose the forest for the trees. So if you're looking down at the small gap between the bark on the tree, you probably don't really know what's happening with the forest as a whole. And right now we're starting to look at the trees, and we're going to start looking at the bark. So you have to be kind of careful because there's always more to look at. But when you start getting down way in the small minutia, the probability of accuracy goes way down. But we're still in a very high probability of accuracy region. All right, so what does this all mean so far? Well, we now have a signal of the first 6 shots that we can look at in depth that shows us just about everything we're probably going to look at. It doesn't tell us what the results will be, but it gives us enough signal now to do our job. And when you play this, and I'm not going to present that audio now, but I will in the ultimate report, you'll hear the hum, even though I've reduced it very prominently. The hum now has been, this region where the background appears to be kind of bluish, that's noise. We've amplified this up so loud, so far that the noise now becomes quite prominent, i.e. the 60 hertz hum and all the other static. Not so much over here. All right. All right, so it showed you generally the regions I'm going to be looking at, not so much in A. And then there's also these other little regions right here between region A and B that I'm going to look at. So let's get into that. So let's look first at the, okay, well, I don't know, maybe I can, let's see if I have anything that's better down here. I'm going to go through these a minute to see if, okay. Oh yeah, here we go. Now this isn't the best picture, but if we look at the 5 shots, because they're they're pretty easy to look at, and you look at on this we have the waveform. Then behind it we have a what's called a decibel squared plot, which basically takes the signal, takes the absolute value of it, i.e., gathers up the positive and the negative in a constructive way, and then squares it. And that's kind of a approximation for power of the signal. And so here we see that you can clearly see these little spikes for shot 2, 3, 4, 5, and 6. You can see that they kind of grow in intensity from left to right, with 6 being the loudest, and you can kind of see that they are broad spectrum. That is, they have some signal all the way from high frequency to low frequency. That's the power spectrum. Okay, if you look at the waveform, you can correlate those peaks pretty well to the peaks of the signal, except that on shots 2 and 3, well, let's go back a second. For each one of these sounds, there is the primary sound and then this tapering off from reverberation. There's also this section that it builds up to the peak signal. Now this is unusual for gunshot acoustics in that normally gunshots start immediately. So there's something going on that causes this signal to build up to a peak as opposed to just occurring instantaneously. I'm not going to get into why tonight. Just note that it's there. And you'll also note that these things are about the same length and duration. The build up, the peak, and the taper are all about the same duration, somewhere a little bit less than a second. And then over here we have 2 shots, the shot 2 and shot 3, and their build up and while their tapering is overlapping, so some of the signal gets confused and clouded. Okay, but even considering that, we can drop down into the log frequency plot, and for shot 2 we can see that shortly after it there's this kind of a strong blippish thing, and for the other shots we can kind of see, if we look down here at the contrast, it's easier to see. We see that shortly after the main peak there's a smaller peak. Here's the main peak, there's the smaller peak, here's the main peak, here's a smaller peak. So there's some structure there, and we can take advantage of that, because now we know that all of the 5 shots, even though this one's kind of confused, they're still the same structure, have this small buildup, they have a peak, and then sometime after they have a smaller peak, and they taper off over almost a full second. And we can use that to ask the question, what should shot 1 look like? Well, it should look the same, shouldn't it? All right. But does it? Good question. Here's what shot 1 looks like. Okay, well, what do we have here? Well, the peak, first off, the signal is much weaker. Second off, we have a whole bunch of stuff here. We've got a fairly sharp onset at this region right here. The peak occurs a little bit later, but we don't have a good taper. It starts to taper and then something else happens, and over here we have something else. And then the build-up, there was no extreme, there was a little bit of build-up but not extreme, and on amongst all that you can see all these little peaks. So you have to start asking then, what's going on? So we drop down into the spectral contrast, and we see that here's the major peak, identified probably as the muzzle for the first round. Sometime later there's a bigger peak, but in between there's another one. And then over here we see a signal which is almost as large, if not larger, than that primary peak, and it's beyond a second. I don't show the scale here, but that's beyond a second. So now we start to wonder, and it too has this fine structure in it, just be it reduced, a little bit after and then in between. So at the point, let's see, 0.16 about is the big structure. In between them is about well, let's call it 80 milliseconds between these small ones and 160 between a set of two, which if we go back over to the 5 shots, we see that there is structure between some of these. For example, on shot 5 and 6, we'll have the primary, and then we'll have one a little bit later, about 80 milliseconds, and then about 90 milliseconds after that, the bigger one. And it's kind of similar there. Not so much on shot 4, but there is some on shots 2 and 3, even though they are overlapped and clouded. So we go back over to the first shot here. We can see that yes, there is structure, but there appears to be another structure here, and this buildup appears to have structure to it too. So what the heck are we looking at here? So now we have a real controversy. I haven't resolved this controversy, but at this point in time, and I've looked at this, and I have a whole bunch of notes. Let's see, where are my notes? Okay, my notes, yeah. I've, looked at all these things here, and I've come up with the conclusion that I believe there were more shots fired. I can't prove it yet, and I can't explain it. And so what are the consequences of that? Where are those shots? I believe that this is what we classically call the first round, and I believe that there's a round after it and there's a round before it. And those don't produce a projectile that's supersonic, because I don't see it on the other 20 videos that I looked up, but I'm going to go back and review that. So at this point we have a controversy. Why would there be 2 shots that didn't produce a supersonic projectile that we could record the Mach wave for, either on this video or on all the other videos? And why would those have been fired? Who could have fired them, and how? Well, the first thing, okay, so I've identified a maximum of 2 extra shots in addition to the 6 known, so that's a total of 8 shots. Now that's possible, probable, and maybe it happened. Can't say for sure until there's corroborating evidence, because this in fact could be some sort of weird echoing. I don't think so, but it could be. So there's further research needed here, but when you think about this logically, the guy marked, what did I say, 13 shots total. That would mean there are additional 7 shots. There aren't an additional 7 shots here. I don't care what you say, how soft the signal might be. There are not 7 extra shots here, because these little individual fine structure peaks are a function of the reverberation, as we demonstrated with these over here. If you counted each one of these little things as another round, you'd have a multitude of shots which didn't occur. And that's what's happening, I believe, for these little 3 areas. That's just the reverberation. But there's enough gap here and too long a gap there for these to be, I believe, to be part of the same signal. Is it possible that 2 shots were this close together? You bet, because shots 2 and 3 were that close together. So that's entirely possible. Could he have been using the rifle to break out the window? Maybe. If he wasn't and the hole was already there, why don't we hear these supersonic cracks? I don't think any subsonic ammunition was used by anybody at any time during the entire massacre. So, to me then, there's something that happened just prior and just after the first round that needs to be investigated that may indicate 2 additional rounds were fired. So we'd have to have casing support that, and I'll have to go back and look at my casing count. But the problem is we don't know precisely, or at least I don't, how many rounds were fired through the door, because it's all confused between what happened with Campos and what happened with Schuck. But I will go back and try to reconcile it all. The thing to note here, the intensity. When we started here, I noted that the intensity of the signal intensity for the first 6 rounds was orders of magnitude smaller than the intensity for volley 1, and that even amongst the first 6 shots, the intensity of the first shot was an order of magnitude less. Now, I've talked to you about how the signal gets attenuated coming out of the window at large angles, like the 90-degree angle coming down. I've explained to you how the overhead, briefly, how the overhead structure reduces the signal, how a rolled up window reduces the structure, how coming out of the room reduces the structure just because of the size of the aperture of the window. I believe that when the shots were fired, that the difference in intensity between shot 1 and these other 2 possible shots, and shots 2, 3, 4, 5, and 6, is due to more of the glass being blown out by the pressure of the muzzle wave. That's just my personal interpretation. I don't have any way of proving it at this point in time, but it makes sense. Alright, so that's a lot to reveal so far, but let's go ahead and finish up what the rest of the sounds in this region sound like. We've got a couple more things to look at. First off, prior to even these first things, we have 2 low frequency sounds right here. And these sound like very low volume booms. But you know what? I can't make them out and distinguish them from the background music. So when you listen to this at very high amplification, and when I provide the .wav file for very high amplification, it almost sounds like there's two explosions in the distant background, because the width of these is too large for a standard muzzle wave, but it's too short to be any signal that came from room 132 and 134 and 135, because there's not enough reverberation, and they're too sharp and clear in many cases. And so at this point, while it sounds like booms from something, I don't think they are. I think they're just sounds coming from the car or the music. So let's go on to the music, because there's going to be something really fascinating going on here. So music in the background. There we are. There's 2 regions of music. One occurs, well, let's see. Let's go back to the introduction. One is region C, and the other is region E. Region C is lower volume than region E. But if we take region E and we amplify it up and we look at it at 8, so here we see 5. These are the 5 tail end shots, shots 2, 3, 4, 5, and 6. And then we have this sound, which is most definitely something happening with the door or some other sound. It's not anything that coming from room 132 and 134 or 135, because any of those sounds would have to produce this reverberation, and this is just a clean. So this is a local sound produced locally inside the car, as are all these other nice clean little spikes. Now, when we take the log frequency plot and we ask to look at it at frequency emphasis, not time emphasis, we see some structure that is just plain fascinating. So over here on the right hand side are, let's see, I really want green this time, so we'll go green, is the music. All this to the right is the music. Now this band right here that's, kind of dark, that's a result of the fact that I filtered out both the 60 hertz noise and part of the noise. But what I want you to look at here is that we have a very regular and repeating structure, both at this low frequency. You'll see that this, I'm going to mark below these, there, 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 here, and here. Okay, so at the low frequency range, in the low end of the frequency bands, you'll see that there is some pretty regular sounds produced by the music, and in this case, this signal, let's mark the overlap, overlaps with, that would be shot 5 and 6, not so much shot 4, but then we have, there's some on shots 2 and 3, you'll see that there's some interference going on. So at the low frequency end, the music is producing interference with the gunshots and making part of the signals appear brighter or more intense than they would be without the music. So we're going to have to look, so some of this stuff down here on the spectral contrast is being caused by the music. And similarly, up here at the higher frequency, whoops, well, they don't care what they mark with yellow, you see that there's also some peaks going on. Now, it's not so clear or prominent over here, but that high frequency could be clouding the upper end of the frequency for the shots also. And that, let's see, I believe that I have the sonic visualizer session open for that. Let's take a look. Yeah, and let's clear all the noise. Yeah, so here is the, oh, this is, oh yeah, okay, so here we have, let's go over to the 5 shots. Okay, now this is a different coloring, but here you'll see in these regions those little drops for the lower frequency, and it continues on, and then up there on the top you'll see them up there. That kind of screws me up, but anyway, up in that frequency, and these are for the 5 shots. That's what we displayed. But if we roll it over to the first shot region, and once again you can see that that bright demarcation, let's mark it with blue, oops, I want to write blue right there. You'll see that that bright demarcation in the background noise is the point at which I applied a greater amplification to the left side and lower to the right. So the sound became much, much louder. Alright. But anyway, let's go back to that. And you can see that that sound, this is the, let's see what color I want. Let's go pink. That low frequency thing produced by the music continues on into the region associated with, I lost it there, that looks like something right there, associated with the first shot. And so part of the signal here then is being altered or shaped by the background music. The further we go to the left, the less it appears to be so. The further right we go, the more it appears to be. Which, you know, I don't know. It's neither here nor there. But it still doesn't explain everything as to why there's these extra shots. Although here it might. You see right in this region where there's kind of a peak in there, that might be exclusively music. So that shot ahead of the first one might be explained partially by music. But then again, I don't think so. Oh, no, I'm wrong, because here it's right there, and the music's ahead of it. So this stuff there is music noise. This is that first shot that we don't know what happens. This is the actual first shot, and then that's the second little shot that I think exists, but didn't produce a supersonic projectile, and therefore the bullet should have been lodged in the glass, or fell out the edge, or dumped off somewhere way ahead of the prior to the venue. All right, let's see. What else do I want to cover? Now, let's erase our scribblings. Let's get back over to the. Well, that's enough on the first shots. there's a whole lot of stuff to do here. One of the other major things to come out of this research is the fact that, let's go back up to, there's so much stuff I have to search sometime. Route, let's look for route. Okay, taxi travel route. And then the next one down. Look at the whole goddamn thing. There we go. Scrivener is great for organizing stuff because you can, just drop in anything you want, and then you can go back over here in the outline and just drag and drop and organize it that way. And then when you're all done, hit the compile, and it produces a document in any format you want. However, it's not very good for layout. If you want to do professional layout, you have to take and get another program to apply to the final result of Scrivener. Now anyway, back to the volleys. For the most part, the first 6 shots were in a static location, i.e. the car moved very little. But for all the other volleys here, the car was moving between 7 and 10 miles per hour. As you move, depending upon whether you're heading towards the source of the gunshots or away from it, your timing will change accordingly. If you're moving away from the, let's say for example like with volley 4, where you're moving away from the Mandalay Bay, and therefore at each moment you're increasing the length that the muzzle wave has to travel, the time it takes to get there is longer, and therefore the sound from each round, the muzzle wave from each round, will arrive just a bit shorter, or take a bit longer to get there. So when you compare that to, say, a recording up here in the venue that isn't moving, you'll see that the duration of the volley, based exclusively on the muzzle waves, is longer. Now, on the other hand, if you were going towards the shooter, then the duration of the volley would be shorter. And you can I can and have done very precise measurements on volleys 1, 2, 3, and 4, and you can tell conclusively that there were no shooters on the ground, that there was no shooter in the tram, that for volley 1 it was approaching or shortening the path. For volley 2, the first half of it was shortening, and then volley the rest of it increased it in a way that could not happen if the shooter was located inside the tram. And similarly for 3 and 4, a similar property. So it's all consistent with a shooting occurring out of room 32135. In fact, the details are so accurate that you can predict very precisely. Let me back up very precisely. Previously I've made the statements that plus or minus 150 feet. Well, with this video, I can nail it down to within 30 feet. And that's a whole nother report. We're requiring many pages of calculations to show. But that's the bottom line, is I no longer need to worry about where exactly it came from, room 32135. No ifs, ands, or buts, except for, of course, the 308 shots. They came from a different area. All right. Well, I don't think I really want to talk too much more about this tonight. There are other revelations that will come out of this analysis. And I sure wished that I had that other segment which covered the time between volleys 1 and 2. And I sure wished I had this segment that, that taxi driver had to come in here, and it probably took 2, 3, maybe even 4 minutes to drive, along westerly along Mandalay, and come in and come around and go under and all the way to where the first shots was recorded. And it would be nice to get those, because we'll be able to make a whole lot of assertions about what did or didn't happen prior to the first shots and between volleys 1 and 2, which I think would wrap up pretty much everything there would be needed to know about gunshot acoustics for the early shots and volleys. All right. It'll be quite a while before I publish the final report. I might do some small pieces prior to publishing the report. But for now, I don't know if those 2 phantom shots are real. I don't know whether I can back them up from other audios. I'm going to go do some deep diving on that here in the next couple weeks, and I hope to see you in a month. All right, grab you in the next one.